So I'm going to work my way through the May 2020 chemistry paper, foundation level, going through the answers, explain what the answers should be, and you should mark your paper as you go along with me here. Question number 1 is all about the elements in group 7 in the periodic table, and provides you with a table of information about the melting points of those elements in group 7. It asks you to state what state bromine is at 100 degrees Celsius. And what I do to try and help you with this one is, first of all, I identify the one I'm looking at here, which is bromine, and I write out those numbers as they would be in order, like this. I know that below -7 it will be a solid, above -7 it will be a liquid, and above 59 it'll be a gas. And then I'll just work out where 100 is going to be there. I know 100 is going to be above 59, so I know it's going to be a gas, so I can tick that box. Question 1.2 says, what temperature does chlorine gas condense to form a liquid? I'm looking for the boiling point of chlorine, which is -35. You can see here. So I'm going to write -35. Question 1.3 says, going down group 7, the melting points do something. This is because the size of molecules increases, so the intermolecular forces do something. Well, if we look at our table again, the melting points as we go down the group here are going up, because those are negative numbers. Remember, they're getting higher, so they are increasing. And this is because the size of the molecules increase, and we know that bigger molecules mean the intermolecular forces also will increase. Question 1.4 showed you this image that you have here and asked you, why did the teacher do this investigation in a fume cupboard? We know we have chlorine gas involved in this reaction, and chlorine gas is what's coming out of our substance and going into it. Chlorine gas is obviously going to be a problem here. The fact that it's coloured isn't going to be an issue, because that doesn't make any difference. The fact that it's flammable may be an issue if you're working in a place near open flames, but it's more likely going to be that it's toxic in this condition. It's actually not flammable as well, so that's also a reason why it's not going to be that one. Question 1.5 says the word equation for a reaction is iron plus chlorine makes iron chloride. What happened to the mass of the glass tube and the contents during this reaction? And give one reason for your answer. We would say that in this reaction, we're going to say that the mass has increased. And we're going to say this because we know that chlorine will start off as a gas. So when you measure the mass of those substances, the gas is not going to be a part of it. But when you measure the mass afterwards, the chlorine will have reacted with those substances and will now be part of the solid. So the chlorine is now part of the solid. And that's the reason why that mass is going to increase here. Question 1.6 says fluorine is above chlorine in group 7. Predict what you observe when fluorine gas reacts with iron. Well, we know that fluorine's above chlorine, and we should also be aware that anything above chlorine is going to be more reactive, because in group 7, the higher you go in that group, the more reactive they become. So if iron burns vigorously, then our fluorine will burn very vigorously. We could also say violently. We could say it burns brighter, with a brighter glow. We get a flame, or even that it explodes. Any of those would be reasonable responses to work with here. For question 1.7, you're asked to complete the balancing of this symbol equation, where we know that we have 2 times everything here. So we've got 2 lots of 1 iron, and that's why we've got a big 2 in front of this iron over here. And we've got 2 lots of 3 bromines. So we've got 6 bromines in total. So what do I need to multiply 2 by to get 6? I need to multiply it by 3. So I'm going to put a 3 there. Question 1.8 asks to calculate the relative formula mass of iron bromide. The relative mass of iron is 56 and bromine is 80. Well, I've got 1 iron. So 56 times 1 is 56. And I've got bromine, which is 80 times by 3. And that's going to be 240. I'm then going to add those 2 things together, and this will give me an answer of 296 as my relative formula mass. Question number 2 asks you to read through these questions about models of the atom. The atoms were first thought to be tiny spheres that could not be divided. Which particle was discovered to change this model of the atom? Well, we know that The electron was the first of these to be discovered, because when we look at the plum pudding model, it's the only one that you should remember there being in that model, and that's the first model we know about. Question 2.2. If you look at this one, it looks a bit like a cookie, but back in the olden days, it was a more common dessert to come across was a plum pudding, and so they named this model after that plum pudding model, which is why it has that name. Question 2.3. In this question, we've been asked to say whether scientists find particles are gold atoms, and you're asked to explain what particles they were, and you should know from your physics lessons that they were alpha particles, and that's the one we should be putting our answer by. We know neutrons wouldn't be attracted or repelled by anything, so they're not going to be the answer here, and that's the reason why that's not the case. Question 2.4 said, which scientist first suggested that electrons orbit the nucleus at specific distances? And that should have been Bohr. We know that Mendeleev was responsible for the periodic table, and James Chadwick was responsible for the discovery of the neutron, so it wasn't going to be him also. The next question, 2.5, says the model of the atom used today has 3 subatomic particles, electrons, neutrons, and protons, and you had to complete the sentences here. It says atoms of the same element have the same atomic number because they have the same number, and which should be the same number of protons. Atoms of the same element can have different mass numbers because they have different numbers of neutrons. Because the mass number is the number of protons and neutrons, we know the number of protons must be the same, so it has to be the number of neutrons that changes in an atom to affect its mass number. Atoms have no overall charge because they have the same number of protons, which are positive, and electrons, which are negative, that balance out that charge overall, and that's what those answers should be. In this question, it says the radius of a nucleus is approximately 1 times 10 to the power of minus 14. The radius of an atom is approximately 1 times 10 to the power of minus 10. A teacher uses a ball of radius 100 centimeters to represent the nucleus. What could represent the atom on the same scale? So we're going to look really here at the difference between these two, and we can see there's a difference of 1 times 10 to the power of minus 4, or about 10,000 times the difference between these two. And what that means is that the nucleus is 10,000 times smaller than the atom. So if our ball is 1 centimeter, we're looking for something 10,000 times bigger than 1 centimeter. We know 10 centimeters is just 10 times bigger. 100 meters would be 10,000 times bigger. So would be the answer that we're looking for here, because 100 meters, we know there's going to be 100 meters, and there's 100 centimeters in every meter, and 100 times 100 is 10,000, and that's the answer we're looking for. 10 kilometers too big, 1,000 kilometers definitely too big. Question number 3 that we're asked to look at next, asked us to complete this word equation for this reaction. Now we've got hydrogen plus oxygen, so you need to think about something you know of that contains both of these things, or we could helpfully read our question, because hydrogen reacts with oxygen to produce water. So hydrogen reacts with oxygen to make water. The answer to that is in the question. You didn't actually need to know anything at all for that question. Question 3.2 asks you to look at the reaction profile and add labels to each of these things. You should know what these 2 labels represent, because we've been over these, or you will have been over these a number of times when you did activation energy and these reaction profiles in your lessons. You should know that Z is the progress of your reaction. You should know that W is the energy. You should know that Y is the overall energy change. And you should be aware that X is the activation energy. These are all things you will have covered when you did this, and you just need to learn about reaction profiles. Question 3.3 says the reaction between hydrogen and oxygen is used in hydrogen fuel cells. What's the reason for using this reaction in a fuel cell? The reason we use this reaction in a fuel cell is because it produces a potential difference. Question 3.4 says a student investigated the voltage produced by a chemical cell. The student used different metals as the electrodes in the cell. The metals were copper, iron, and magnesium. Which two metal electrodes would produce the greatest voltage? Well, we know that voltage is also called potential difference, and the potential difference is the difference in energy between two things. So we're actually looking for the two of these which have the biggest difference in reactivity. And we should be aware that group 2 magnesium is the most reactive of these. Group 2 magnesium is the most reactive of these, and our copper is the least reactive of these. So our two elements to have are magnesium and copper. And it's because they have the largest difference in reactivity. That's the reason why we choose those. Question number 4 is a question all about electrolysis that we're going to look at next. So we need to look at this question and say what observations we make at each electrode if the hypothesis is correct. Let's go read through the hypothesis. The electrolysis of a salt solution produces a metal at the negative electrode and a gas at the positive electrode. We know that we have graphite electrodes and a salt solution. So a metal at the negative electrode and a gas at the positive electrode. It doesn't tell us what those things are, but we do need to be able to say what we'd see. Well, if a metal's going to be produced somewhere, we know that we're going to see a solid being produced at this electrode, some kind of solid. It probably changed colour. You could mention this here as well. Might go silver, something like copper might go like a browny orange colour. That's really obvious. And if a gas is being produced, we're going to see fizzing. We can see bubbles. We could also say effervescence. You can't just say a gas being produced because that's in the question. So we have to say what you're going to see. Well, you're going to see fizzing. You're going to see bubbles at the positive electrode in this question. Question 4.2 said, which salt solution in table 3 does not match the student's hypothesis? So we're looking at which of these does not produce a solid at the negative electrode and fizzing at the positive. Well, all three of these produce a gas at the positive electrode. So we're going to work out our answer here by looking at the negative electrode. We're going to see a solid because copper forms. We're going to see a solid on this one because copper forms, and hydrogen would not be a solid forming. So our salt is potassium nitrate, and the reason why that is because hydrogen is not a metal. You could also say hydrogen is a gas, so you wouldn't see the solid forming. It's also fine as well. Question 4.3 says, give 2 reasons why graphite's used for electrodes. Well, we use it because it's inert. You should know what inert means. You could also say what it means as well. You could say unreactive because that is what it means. And you could also say another reason we use it is because they conduct electricity. You could also mention that it's got delocalized or free electrons instead of saying it conducts electricity, because that means the same thing. There's nothing wrong with you saying that. Question number 4.4 says, what happens to the purple-coloured ions involved in the reaction you have here? We better read through the question fully. A different student investigated what happens during electrolysis. Figure 5 shows the apparatus they use. The purple crystals contained colourless positive ions and purple-coloured negative ions. The purple crystal dissolved in the electrolyte solution. I want to know what happens to the purple coloured ions. Well, the purple coloured ions are negative, so we know that those negative ions will be attracted to the positive electrode, and the reason is because the opposite charges attract. If you want to be really specific, you could say that the positive electrode attracts the negative ions because of their opposite charges. Question number 5 asks us to look at this question. It's about aluminium and says aluminium is a metal. Draw one line from each property of aluminium to the correct reason for that property. One line from each property. So we have to say, why does aluminium conduct electricity and why has it got a high melting point? We know that aluminium is a metal, so it'll have metallic bonding. Why do things with metallic bonding conduct electricity? It's because of those delocalized electrons, that sea of delocalized electrons that they have. And why do they have a high melting and boiling point? Let's see which of these best fit our answer. Has layers of atoms which can slide over. It does have those, but that actually explains why it's malleable and not anything to do with its melting or boiling point. It doesn't have intermolecular forces at all because it's not covalent it's not molecules. It doesn't have a random arrangement of atoms when it's a solid. It's actually going to be that it has strong metallic bonds. Question 5.2 says aluminium can be used to make alloys. What is meant by an alloy? Well, an alloy is a mixture of metals. Aluminium is extracted from bauxite. Bauxite is a mixture which contains aluminium oxide. Aluminium contains between 15 and 25% aluminium. Aluminium oxide always contains 53% aluminium. How does this show that bauxite is a mixture and not a compound? We know that in compounds, the amount of substances involved in them tends to stay the same every time you use them. So for example, in sodium chloride, there's always going to be 50% sodium and 50% chlorine. Because the amount of aluminium in bauxite changes or is variable, amount of aluminium in bauxite the amount of aluminium in bauxite is variable, it varies. We know it's then not going to be a compound because it has to be the same amount every single time in a compound. Question 5.4, it says suggests two problems with storing the waste materials in lakes of mud. The waste materials of bauxite is stored in lakes of mud. The lakes of mud are held in place by dams. Figure 6 shows one of these lakes that we can see here. Suggests two possible problems with storing the waste materials in lakes of mud. We could get leakage of toxic substances from the mud into the environment. We could get water pollution because it's near the dam. We could have damage to habitats. All of these are acceptable answers. You just need two of them. We could end up with visual pollution. We could have the dam blocking light. It could reduce the value of houses that are nearby. All of these are good answers. You could also mention the fact that there could be an unpleasant smell. So that's another possible answer. You could I'm not going to write those down, but there's three good ones. Question number 5.5 says the formula of cryolite is Na3AlF6. Give the total number of atoms in the formula, or the number of atoms we're going to add together the total number of atoms of sodium, aluminium, and of fluorine. I know I've got 3 aluminiums because there's a little 3 next to the Na. I've got 3 sodiums because I've got a little 3 next to the Na. I've got 1 aluminium as there is no number next to the Al, and I've got 6 fluorines because there's a 6 next to the F. So I'll do 3 plus 1 plus 6, giving me a total of 10. What's the reason for adding cryolite to the aluminium oxide? We should be aware that it's to lower the melting point of the mixture. Question 5.7 asks you to choose answers from the box here. When the molten aluminium oxide and cryolite mixture is electrolyzed, the product at the positive electrode in aluminium oxide is going to be whatever is negative aluminium and oxygen, which is oxygen. The product reacts with the positive electrode because the positive electrode is made of carbon. We know that carbon and oxygen will react with each other. Question 5.8 says a sample of bauxite contains 25% aluminium. Calculate the maximum mass of aluminium that can be extracted from 300,000 kilograms of the sample of bauxite and give your answer in standard form. So the sample of bauxite contains 25% aluminium. So the maximum amount of aluminium that can be extracted from that sample of bauxite is a quarter of its total mass. So we need to work out what a quarter of 300,000 kilograms is. So we're going to do 300,000 multiplied by a quarter. And this will tell you that your answer should be 75,000. Now we know our answer should be in standard form. The standard form needs to start off with a number that is between 0 and between 1 and 10, sorry. So here we have got 75,000. What could I do to that to make it be a number between 1 and 10? Well, if I divide this by 1, 2, 3, 4, 10,000, I would end up with 7.5 times 10 to the power of 4 as my answer, because 10 times 10 to the power of 4 is times 10 4 times, which times you're basically timesing it by 10,000. Question number 6 showed you the formula of this compound, and you had to complete the molecular formula of citric acid. They've already counted out the carbons for you. The next thing you have to do is count out how many hydrogens there are, and there are 1, 2, 3. In fact, you can just cross them out. 4, 5, 6, 7, 8. Have I missed any there? No. So it's C6H8. And then I've got to count out my oxygens. I've got 1, 2, 3, 4, 5, 6, 7. Have I missed any oxygens? No, I've got all of them. That must be the compound's formula then. What type of bonding in this is this? Well, if I look at this compound here, I can see that carbon, hydrogen, and oxygen are involved, and all of those substances are non-metals. And I know that non-metals will have covalent bonding. Question 6.3 says, Figure 8 shows two representations of one molecule of citric acid, A and B. Give two advantages of representation A compared with representation B is what I've been asked to do here. So I'm going to look at those molecules very quickly and think about what's better about one than the other. What advantages of A, what's better about this compared to this? Well, first of all, in A, I can see single and double bonds. I can't see any double bonds at all in diagram B, so I know that's a problem that we have there. The other problem I have here is I've got different atoms and they're different colours, so I know there's different substances there, but I don't know specifically what they are. And so A shows which atom is which element. Next question says, a student investigated the temperature change during the reaction between citric acid and sodium hydrogen carbonate solution. Citric acid is a solid. This is the method they use. Put 25 centimeters cubed of sodium hydrogen carbonate solution in a polystyrene cup. Measure the temperature of the sodium hydrogen carbonate solution at 0.25 grams of citric acid. Stir. Measure the temperature of the solution and repeat steps 3 to 5 until a total of 2 grams of citric acid has been added. You can then see the results of the practical in the table. And it says, how did the results in table 4 show this reaction is endothermic? We know that endo means that energy is going to go in to our substance, into our compound, so the temperature should be going down here. And you can clearly see it starts at 22.6 and goes down to 20.6. So our temperature decreases. 6.5 says the three of the students' results are plotted in figure 9. A line of best fit is drawn for these points. The next thing you should do is plot the data from table 4 on figure 9, draw a line of best fit for the points you've plotted, and extend your line of best fit to meet the line of best fit already drawn on figure 9. So we should look back at our results and plot these. So 0, it's 22.6. So I find 0 and I go up to 22.6. So 22 is here, 23 is here. There's 10 boxes between, which means 22.6 would be there. And it's 22.2. No, 22.2. Then it's 21.8. Then it's 21.4. Then it's 21. Then it's 20.6. My final point is to extend the line of best fit to meet the line of best fit already drawn. So I can draw a line of best fit that starts at my first point, goes through all these, and meets up that one. Again, you do that one with the ruler because that's really clearly a straight line for you to use. And if you've done all that, you'd have 4 really easy marks. For the next question, we're asked to determine the overall temperature change for this reaction. We know the reaction stops happening when the temperature starts to go up here, because no reaction is going to suddenly become exothermic partway through. So we look back at our results up here, and we can't see when it stopped changing and going up, so we'll have to use our results on the table. We can see that it stopped going down here, which is 20.2. So we're going to do 22.6, take away 20.2. And this should give you an answer of 2.4. Importantly, if you had redrawn your graph incorrectly here in some way and you had a different point before it starts to go up, you could use those results if you've misread the graph incorrectly and still get 1 mark here out of the 2. Question 6.7 said, what is the dependent variable for this investigation? Well, if we look at our graph that we have here, we can see the dependent variable on the y-axis, where it should always be. If we look at our results table over here, we can see our dependent variable on the right-hand side, where it should always be. So we know that the temperature is our dependent variable. Question number 7 says, the student questions about acids, bases and salts. Zinc nitrate is a salt. A student produces zinc nitrate using an acid and a base. Which acid should the student use to produce zinc nitrate? Well, we know that the acid determines the second name of a salt. So nitric acid is the name of the acid you would use. The next question you were asked is, which is a base the student could use to produce zinc nitrate? We're looking for a base here, so we're looking for an insoluble solid to work with. Zinc chloride is soluble, so it's an alkali, not a base. Zinc sulfate is soluble, so it's an alkali, not a base. And zinc oxide is the only one of those that is insoluble for you to work with. Oxides tend to be insoluble. Other salts tend to be soluble. So that's the reason why that's not the answer. Question 7.3 says, name the salt with the formula MgBr2. Well, we should know what Mg stands for and that Br is for bromine. And when it comes to salts, we don't change the name of the metal at all. And our non-metal goes from being bromine to being bromide. If that was MgCl, it'd be magnesium chloride. If it was MgF, it would be Cl2 or F2, it'd be magnesium fluoride. We always change that second name to IDE because the bromine is by itself. Question number 7.4 is based on this description of a method that you can see here. It says a student investigated how pH changes during a titration. This is the method they use. Put 25 centimeters cubed of hydrochloric acid into a beaker, measure the pH of the hydrochloric acid. With a pH probe, add 1 centimeter cubed of sodium hydroxide from a burette, swirl the mixture, measure the pH of the solution, and repeat steps 3 to 5 until a total of 30 centimeters cubed of sodium hydroxide solution has been added. It then shows you the results, and your question says, describe how the pH of the mixture changes as sodium hydroxide solution is added to the hydrochloric acid, and use data from figure 10 in your answer. Figure 10 is our graph. So you're going to have to use data from this graph in the answer that you give as you describe the pH change. We're going to start off by talking about this initial section from 0 up to 20 centimeters cubed. We're going to talk about the fact here that from 0 to 20, the pH increases. The next section we're going to talk about is at 20 degrees, where something's clearly happening. And we can see that at 20 centimeters cubed, so not 20 degrees, our pH goes from 3 and it goes all the way up to 11. And finally, from 20 up to 30, we again have a gradual increase. It's just about identifying those three sections of the graph that you want to talk about. Something's happening here. This is clearly a section to talk about because something big happens here and something else is happening as the final portion of the graph as well. I know there's going to be three sections to talk about here because if I look at my marks, I've got 3 marks, so 3 sections for me to talk about. Question 7.5 says, what volume of sodium hydroxide is needed to neutralise 25 centimetres cubed of hydrochloric acid? I'm going to look back at my table here and look at the volume of sodium hydroxide that I added when neutralisation occurred. I can see that was at 20 centimetres cubed. Question 7.6 says, figure 11 shows the colour of universal indicator at different pH values. It says the student could have used the universal indicator instead of a pH probe. Determine the colour of universal indicator when 10 centimetres cubed of sodium hydroxide solution had been added to 25 centimetres cubed of hydrochloric acid. Again, we need to go back up to our results table here and look at the pH it would be when 10 centimetres cubed had been added. We're looking at a pH of between 1 and 2. And we know that between 1 and 2, we're going to see a red colour. Question 7.7 says the student used pipettes to measure 25 centimetres cubed of sodium hydroxide. Figure 12 shows a pipette. The pipette is labelled 25 plus or minus 0.06 centimetres cubed. Calculate the percentage uncertainty in the volume measured using this pipette and use the equation you've been given. These will always measure 25 centimetres cubed and the uncertainty is going to be 0.06. So we're going to do 0.06, our uncertainty, divided by 25 times by 100 to get our answer, and you should end up with an answer of 0.24%. Question 7.8 says, give one advantage of using a pipette rather than using a measuring cylinder to measure the volume of hydrochloric acid, and it's because the pipette measures volumes more accurately. This is a fancy dropping pipette specifically. If you're going to talk about them, the little plastic ones we tend to use in lessons are also pipettes, but they're less accurate than these. Question number 8 says, this question is about structure and bonding. Which two substances have intermolecular forces between their particles? We're going to look through these and identify which of these are actually molecules, because only ones that are molecules will have intermolecular forces. So we're looking for covalent bonding, and we're looking for small molecules. Diamond is covalent bonding, but is a giant molecular substance, so no intermolecular forces. Magnesium would be ionic, wouldn't be ionic at all. It'd be metallic bonding because it's a metal, and that means it's got electrostatic forces of attraction. Polyethene is a polymer, so it's actually a very long chain of ethene molecules joined together, and this means it's going to be lots of long chain molecules near each other, so it will have intermolecular forces. We know ethene is covalent, and that's going to tell us that as well. We have sodium chloride, which is a metal and a non-metal. That's ionic, and that means it's going to be electrostatic force of attraction, not intermolecular forces. And we have water, which is also going to be a small molecule as well. I knew there was going to be 2 answers here because, again, worth 2 marks, and also tick 2 boxes. Question number 8.2 provided you with this image that you can see of 3 different compounds and their structures. Your job was to look at them and you were to compare the structures and the bonding of the 3 compounds. Well, if we look at them, you can clearly see in these diagrams, carbon dioxide we know to be 2 non-metals, and we know this is going to be a small molecule based off this structure that you can see here. So carbon dioxide is small molecular covalent. And we know that magnesium oxide is going to be a metal and a non-metal, and we can also see there's ions involved here, so it's going to be ionic. And we know that silicon dioxide, based on this structure here and the fact that it's non-metals, giant covalent. Other clues we've got is we have these lines going off which are clearly showing, well, this joins to a bigger structure as well. So we have small molecular covalent, ionic and giant covalent structures to talk about here. Well, what can we compare easily to start with? If we look at carbon dioxide, magnesium oxide, and silicon, we can see that magnesium oxide here has ions, and these two have got atoms. So let's make that our first point. We're going to mention that magnesium oxide has ions. And carbon dioxide and silicon dioxide have atoms. If we look at magnesium oxide, we can see the lattice structure that it contains. Now we know lattice structures are giant structures. We know silicon dioxide makes a giant covalent substance. Both of these are giant structures, whereas carbon dioxide is only small molecules. So you could also mention the intermolecular forces involved here if you wanted to, because that is something else that you wouldn't get in those giant structures. They're just going to be bonded together by electrostatic forces in magnesium oxide and by those covalent bonds in silicon dioxide. We'll come back in a second. Now, covalent bonds and ionic bonds are all strong bonds, so we could mention that first of all. So all three compounds have strong bonds. But we're going to mention first of all that CO2 and silicon dioxide are non-metals. And that means covalent bonding. Covalent bonds means electrons are shared. We could also mention here we can also mention here the bonding in magnesium oxide. So our magnesium oxide is a metal and non-metal. And that means that we're going to have ionic bonding. We're going to have electrons being lost by our metal and gained by a non-metal. We could also look at the number of bonds involved. We can see if we look at silicon dioxide, you're only seeing single bonds in here, whereas carbon dioxide has double bonds. These are all points we can make. So silicon dioxide only has single bonds, whereas carbon dioxide has double bonds. Specifically, every silicon has 4 single bonds. It's also worth mentioning for marks here in this question, because this is it's a 6-mark question. They've actually leveled this question. For level 1, you just have to mention any features at all and the differences between them noted, whereas for level 2, you have to mention relevant features and clearly identify some ways that are similar and ways they are different as well for full marks in the question. Question number 9 says the question is about metals and the reactivity series. Which 2 statements are properties of most transition metals? We had to read through these, and you should know some of these are about transition metals, okay? You should know that ions can all form ions with different charges. If you ever look at a periodic table that are in your science classrooms, you'll see the transition metals have got multiple charges in the boxes with them. and that's because they form ions with lots of different charges. And the important other thing to mention is their high melting points, because they're metals. They haven't got low density. Again, they're metals. They're quite dense. They don't form colourless compounds. In fact, the exact opposite. And these metals are all hard metals like iron, copper, and things along those lines. Question 9.2 says a student added copper metal to colourless silver nitrate solution. The student observed pale grey crystals forming and the solution turning blue. Explain how these observations show that silver is less reactive than copper. Well, we've added pure copper to silver nitrate in a solution. So we're starting off with copper atoms with no charge and silver nitrate being an ionic substance, because silver is a metal and nitrate, nitrogen and oxygen, are non-metals. This will be ionic. So you have silver ions and nitrate ions floating around. We have pale grey crystals forming. Now, pale grey also can be called, is another way you describe silver. So we know that silver is forming. Those crystals we see are silver. So the crystals are silver. They're literally the element silver forming. And that blue solution we're seeing is because copper ions are starting to form. So that means copper is now in the compound. So the copper ions are blue. And why has that happened? Well, that's happened because copper displaces the silver. And it does that because it's more reactive. Question 9.3 says a student is given 3 metals X, Y, and Z to identify. The metals are magnesium, iron, and copper. Plan an investigation to identify the 3 metals by comparing the reactions with dilute hydrochloric acid. You should give valid results in your plan. Now, the first thing we need to identify here and be able to talk about is the idea that each of these are going to react slightly differently, so we should be able to explain which one will react the most vigorously and which one will react the least vigorously. We should know that magnesium is the most reactive of those substances, copper is the least, and iron sort of sits in the middle of those two. What's the actual practical we're going to do? We are going to take a specific amount, and let's not start with take. We're going to measure a specific amount of our metals. Let's say 1 gram. Of magnesium we're going to start with. We're going to measure a specific volume, not the word amount, a specific volume, let's say 20 centimeters cubed of hydrochloric acid. We could also say what equipment to use. We're going to use scales for this one, and we're going to use a measuring cylinder. Or you could measure 25 centimeters cubed, and you could say using a pipette. We've already said that's a really accurate way of doing things. You could use that information here as well. We're going to there's a few different ways you could measure their reactivity here. I'm going to go with measuring how much they bubble when you mix them together. So we're going to add the magnesium to hydrochloric acid. And we're going to observe the bubbling. You're then going to repeat this with your 2 other metals. Now, you could have measured the temperature before you added the metal and measure the temperature after you added the metal, and a higher temperature change would have happened for the most reactive of these. But doing it with bubbling is just the easiest way to see them in the quickest way. If we talk about the results for these ones, we'd mentioned the idea that magnesium will fizz the most. The iron will fizz the next least. And finally, the copper will not fizz at all. And that's all you had to say for your 4 marks in that question. The final question asks you to calculate the relative atomic mass of the metal M. Metal M has 2 isotopes. You can see here, table 6 shows the mass number and percentage abundances. If you're ever given a question like this one, the calculation's always exactly the same. We're going to take the mass number and the percentage abundance of each of those 2 substances, and we're going to add them together. So we're going to do 203 times 30 plus 205 times 70. I'm going to divide that by 100. And this will give my answer of 204.4. If I'd been given multiple percentage abundances and mass numbers, I'd literally just be doing that with all the mass numbers and all the percentage abundances and dividing them by 100 to get my answer.